Hello and welcome to part 1 of Dev Maths and Stats Refresher Course, Lecture 8. Now today we bring together some ideas from probability and from this basic descriptive statistics and random variables. And we start to get at some fundamental concepts that are really essential when you're thinking about areas of risk and uncertainty and how the values of one variable might influence the values you can expect from another variable. Ideas of bias and efficiency, which are going to go throughout your work with statistics and estimation this year. So we start with two really basic ones, expected value and variance. So expected value in the world of probability is really, if you think back to descriptive statistics, it's like the mean, the equivalent of the mean. So the basic definition of expected value is that you add up every possible value of the variable multiplied by the possibility or the probability of observing that value. So each value times the probability of getting that value. So if you've got a discrete random variable, so you can actually write out the list of values. So if these are the possible values, x1 to xn, and the probabilities that go with those are p1 to pn, that the expected value of x is written with a big capital E, x for the random variable, and it's just x1 times p1 plus x2 times p2 plus x3 times p3, all the way up to xn times pn. Often the expected value is also written with this Greek letter mu, which also can be used for the mean statistically. And note that while the mean and the expected value are closely related concepts, they're not exactly the same, but they're closely related. Now, if you look at this, think back to what we did yesterday with the sigma notation. This can be written much more neatly like this. So expected value is the sum for I equals 1 to n of xi pi. If it's not a discrete value, so it can take a whole range of values, say like yesterday we had one between 10 and 30, there's an infinite number of values, so you can't list them. Then the equivalent is that you integrate. And you integrate either between negative infinity or plus infinity, or between the values if you know the range of values it can take. But minus infinity and plus infinity is fine. And then you do x multiplied by the probability density function. So it's very similar to this, and you integrate it instead of summing it. Okay, so that's the background. We quickly get into some rules which help you build up probability techniques and the way that you analyse those and interpret those. Now the first one actually is a really simple one, but it's the one that it's showing this is true takes a few lines, but we can show that if you have two random variables a and b, so a could be the result you get when you throw dice, and b could be something like the number you get when you pick a random number between 1 and 20, and you're going to add those up. I'll give you a more concrete example in a moment, or a more applied example. So what's going to happen when we do this is that we can show that the expected value of the total of those two numbers is equal to the expected value of the first number plus the expected value of the second number. And what I'll do is I'll start writing out how you can show it using this definition here. So remember, what we're looking for is the expected value of A plus B. Yeah. So by definition, that looks like this. So we want to take each possible value of A, which is, we can call AI, so A can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or whatever, how many values there are for A, plus all the possible values for B. So B can be 1, 2, 3, 4, 5, 6, and so on. And then you add those up. Well, no, before you add them up, you multiply by what's the chance of that happening. So it's the probability that you get this value of A and this value of J coming up. So what you're looking at is the joint probability distribution. Or and, so it's probability of getting this and this. What's the probability of that combination? And then what you have to do is you have to add up, go through all the possible combinations of I and J. So you end up with a summation like this. Quite left enough room to do this very neatly. It's a double summation. So you start from I equals 1. Thought it was just a bit too small. You start from I is equal to 1 and go all the way up to, I won't write it this complicated every single time, but just for the first one I'll write it in full and then I'll start making it more abbreviated. So I can't just put n, because what does that mean? I've got to put n a and this one will be nb. So for every value of I that goes from I equals 1 up to however many possible values there are for n, for a, then for each value of I, then you go through all the values of j like we did in the exercise yesterday. And here I'll put n b, because it could be there are different number of values of a and there are of b. For example, another concrete example is you toss a coin, and if you get a tail, you score nothing. If you throw heads, you get 1 point. After you've done that, you throw a dice, and you get the score on the dice. So, what's the expected value of your total score when you've thrown the dice and tossed a coin? To work that out, you'd have to, A would be the score from the coin, 0 or 1. B is the score from the dice, 1 to 6. So here, if A would be going between 1 and 2, because there's only 2 possibilities on that coin, and then for each of those 1 and 2, you'd have to go from 1 to 6 on the dice. And you multiply the total on the coin, 0 or 1, plus the total on the dice, times the probability of getting that combination. Which, because they're independent events, in that case it would be just all of them would be 1 in 12. But the nice thing about this is that it doesn't have to be independent. So the example I thought I'd give you that's a bit more concrete is go back to this example, which is when you have 2 people working, one person working for 2 weeks, and this is the number of days work they get in the first week, this is the number of days working they get in the second week, and remember this is the joint probability distribution, so this is the chance here of this person getting 2 days the first week and 5 the second week, so you've got all the combinations of probabilities here. What I've added on here is the total number of days they get in the 2 weeks, which would be your AI plus BI. So A is the days in the first week, B is the days in the second week. AI plus BI is the total number of days here. So to work out the expected value of AI, BI, by definition, you've got to go through each of these totals and multiply by the probability of that total coming up, which is just this one up here. So what you do is you do this plus times this, plus this times this, plus this times this, plus this times this. So you go along each row, multiplying this row by this row, or you can go the columns, multiply them all together, and that would give you the expected value of AI plus BI, the expected value of AI plus BI. And remember that in this case, the 2 things were not independent. So this rule doesn't depend on the independence. Okay, having said that, let's just go through a couple of lines to give you an idea of how you show that this comes out properly. So the next line of this would be, you'd split this into 2. Now what I'm going to do now is, I'm going to write just that, even just that, sorry. Draw an I. And that's going to mean the whole thing. Yeah, etic. So when I just put the I, that means all the possible values of I, just to save writing all this again and again. So same for J, so that means add up all the I's and all the J's. So what I'm doing here is I'm splitting it up like this. Plus j, probability of AI, B, J. And you can split it up like that because once you expand this out, if you write down a whole list of the things you've got, you'd have, the first thing would be A1 plus B1 times the probability of A1 plus B1. So you can just split that up into A1 times the probability of A1 plus B1, so yeah. So you just expand these brackets out, and then you collect all together all the ones that have got AI in it, so add those up, and collect together the ones that got BJ and add those up, and you get these two separate bits. So just doing the addition in two separate bits. The next thing I'll do is, and this is going to be really complicated, you might follow this very carefully. This is very subtle. You should be able to see what I've done here, which is nothing, because that's exactly the same. I'm just labelling over this because what I want to do is write here J, and this is, seriously, something else happened here, BJ, PAI, BJ. All I've done here is I switched the order of the summation, which you can do because all that means is here I'm going to go, this one here I'm fixing each row and going along the columns like this. Here I'm going to instead fix each column and go along each, I'm going to fix each column and go along each row instead. So instead of adding up like this way, the second one is now adding up like this. But it should come to the same thing. So you can do that. Okay, the next bit we have to do something which is more substantial, which is to remember the conditional probability formula, because it may well be that A and B depend on each other. So in this one I'm going to write it like this. I'm going to do one more thing actually, so try and save a few rows. I'm also going to write this. Because AI, that does not depend on J. So this will be the same. When I fix one, that'll be one running all through these. So I can take that out as a factor, because that'll be repeated for every single one of these. So that just leaves this in here. And this I can write using the sorry, I'm getting ahead of myself, trying to cut 2 more rows out. We do that next. First of all, we have to write this like this. P, B, J, given A, I. Yeah, okay, I think we'll just leave that. Plus, and then this thing here, from here. Now I can do what I wanted to do here. Oh yes, must explain this. This is the conditional probability formula for this and this is equal to the probability of this happening, AI, times the probability of BJ happening, given that AI happened. That's that Bayes rule again. Now, here you do exactly the same thing in this one, except you switch the order around. So you're doing sigma j, sigma I, and this time I'm going to say bj times the probability of bj happening times the probability of AI happening, given that bj happened. So using Bayes' rule the other way to bring out the bj. So you've got the probability next to bj times probability of bj, AI times probability of AI. Now I can do this thing that this part will be constant. So any value of I will be constant, because here we're going to fix an I and then go along the rows. So for that row it'll be constant. So I can just factorise it out and just do that afterwards. So that comes out there. And then what I've got here is sigma j, probability of bj, aj, ai, sorry, And then something very, very similar here, symmetrical except the other way around. So J, B, J. There's only one more around this, so don't lose the will to live. Sigma I, P, A, I. Suddenly it's going to look much more simple in a second. Because the point is here, what I'm doing is I'm saying I'm going to go through all the possible values of J, yeah, and I'm going to say, what's the possibility of getting that value of J given the value of I? So if for example on the dice, if the dice came out as a 0, given they've got a 0, then I want to know, given that probability of getting a 0, what's the probability of getting either a 1 or a 2 or a 3 or a 4 or a 5 or a 6 on the dice? Well, all those probabilities together, I must get one of those. Once I've thrown the dice, once I've tossed the coin, then I know that I'm going to get one of those values on the dice because I'm going through all the possible values. So this total must come to 1 because I'm going through every possibility. So that must just add up to 1. So this just disappears and becomes 1. And similarly here, once I've fixed for any particular value of Bj, the probability of all the different possibilities of Aj, Ai must be 1. So that becomes 1. So this part is just 1, and this is 1, so we can ignore that. And then this here, the sum of all the AIs times the probability of the AIs is just exactly the definition of the expected value of A. This is the expected value of A by definition. Go through every value of A times the probability of that. This is just 1, so it multiplies it. This is the expected value of B. This is just 1. So we find that we've shown that the expected value of A plus B is equal to the expected value of A plus the expected value of B. You can separate it out like that. So that's very useful, very fundamental fact about probability distributions, and we use that a lot. So I hope that this process of explanation makes sense to you, but if not, at least this you must remember, because this is really fundamental. But it's good practice for the sigma notation. Okay, let's just go back and look at the other couple of rules before we get to the end of this first film. The others are much simpler. You'd be relieved to know. So next one down here is just the expected value of k times A is equal to k times the expected value of A. See this very easily. So you want to know something about the expected value of k times A. And k is just a constant, so could k be 3 or 4 or 5 or 6. And it's fairly obvious that if you throw a dice, the expected value of 10 times what you're going to get on the dice is just 10 times the expected value. So as you expect, it's pretty simple proof. K times AI, P, AI. So this is the definition of it, but then when you write this out, you're going to have K times A1 times probability of A1 plus K times A2 times probability of A2. So all of them are going to have K as a factor. So you just factorize this out. And this then just becomes the definition of E. Just becomes that. That is the expected value of A. So as you'd expect, it's fairly obvious that when you multiply a random variable by a constant, the expected value is multiplied by the same thing. And number 3 doesn't even need a proof. It just needs some sort of philosophy. If k is a fixed number, then the expected value of that fixed number, like the expected value of 5, is 5. So unless nuclear fusion or God or someone changes the rules of the universe, the expected value of a fixed number is just a fixed number. Okay, so far so straightforward. Now a couple of further points. One further point: conditional expected value or conditional expectation. And this is what you want to know about when you get down to real applied work, particularly things like impact evaluation. You want to know, okay, what's the expected income of these women in this village? Fine. Okay, but what's the expected income of these women in the village, given that we know that they've joined a microcredit scheme, or given that we know that they have joined a self-help group, or they've had some intervention? has that changed? Because if the expected value of their income is the same with the intervention as it is without the intervention, your intervention is not really very good. And if it's lower, so this is the terminology. EX/Y, EX pipe Y, the vertical thing is conditional expectation of X given Y. It's defined in the same way as before, except you use conditional probabilities like this. Yeah. So expected value of X given Y is go through every value of X and say, multiply that value of X with the probability of Xi given the value of Y you know has occurred. So for this, you know something's happened, so that's altered the probabilities. That's going to alter your expected value. To have another example, consider these two random variables. R is the rainfall, so we don't know what that's going to be. Y is the crop yield. But in a certain rural area, we know that agriculture is dependent on rain, so they haven't got any irrigation, so R is going to have an input on crop yield. Which of these two things would be higher? The expected value of yield or the expected value of yield given that rainfall was high? So pause for a second, it's fairly obvious. And the answer is that we'd expect it's this one. So if we're given this extra information that the rainfall was high, then naturally we'd expect the yield would be high. Yeah, because if you look at those spread of probabilities, the probabilities that are associated with the higher yields will get higher, probabilities with the lower yields will get lower, so we'd have a higher expected value. Of course, as always, it's never certain. If it gets too high, you can have flooding and so on, so that'd be no good. But without any further information, I'd say I'd expect this one to be higher. Okay, that was a surprisingly long section because of this fiddly proof. The rest of them don't need to go on as long as that. But I think we'll put them in another video anyway, so for now, thanks for watching.